I appreciate your coming to hear these talks. I'm Shalom Lappin. I'm a professor of natural language processing here in EECS, that's the School of Electronic Engineering and Computer Science here at Queen Mary. And the school has graciously helped organize this series of talks for me. These are three talks in which I will try and present the main ideas of a book that I actually just finished today. Which is on exactly this topic. That's the title, Understanding the AI Revolution Risks, Imagined and Real. So this talk is going to deal with the following. There'll be a certain amount of technical content in today's talk. Those of you who come from computer science, it'll be baby stuff. For those of you who don't have the technical background, I will try and present it as gently and in as friendly a way as possible. There'll be plenty of time for questions at the end. We'll have a good half-hour session where you can grill me to make clear what isn't clear. And people on Zoom will be invited also to ask questions, which I can hear and then convey to the people there. So I want to talk first about a little bit of history, the early years of AI, which virtually everybody has forgotten about, including me. So when I started writing this book, I began to rediscover things I'd forgotten. Full confession, I started out in AI at IBM in '89. Coming from '89 to '93, I was in the AI department at IBM in Westchester, New York, and I was one of the people who was doing symbolic AI, which is called good old AI, resisting all the positive stuff in statistical and neural network stuff, which I've since embraced, much to the horror of some of my former colleagues. So I want to talk a bit about this so we see where some of the main ideas that have created what I'll call the AI revolution have come through. And more accurately, I think it's necessary to call it a deep learning revolution. And it comes in two phases, and I'll try and sort of fairly quickly indicate what they are, and then conclude with some current applications of AI. That is, there are actually some good things that AI does, and I'll try and summarize those. And then the next two lectures we'll talk about problems of AI, threats and dangers, the stuff that people in the media love to discuss. Yeah.
I think you've lost the audio. Can they still hear you?
You lost the audio? Okay.
It's just crackling a bit.
Hold on. Can you hear me through here?
Just one second.
Sounds like a loose wire, to be honest.
Can you hear me now?
It's not coming through the speakers.
No? Okay, well, here's what we'll do. I'll just speak a bit louder. Can you hear me now?
Yeah.
I do have a reasonably strong voice, or did, while raising kids. Yeah, so the guys at home don't care. So I'll just talk like this, and we'll forget about the mics, as long as the slides are there. And then I'll talk about some conclusions. So next week's talk, I'll talk about imagined dangers, that is, dangers which people talk a lot about but don't seem to me to be real, or at least they're not well motivated. And then the third, we'll talk about real serious dangers, which aren't always addressed and recognized, and issues of public policy, of possible regulation to deal with them. And we'll get into some social and economic issues there. So that's the general outline of both of this talk and of the three talks in general. So here's some history. Turing in '36 laid the foundations for the formal theory of computing, although there, of course, is much earlier work that dates to right through the history of logic and mathematics through Babbage and Ada Lovelace, who could be credited as the first software engineer in the 19th century. But modern computer science, I think you can, from the mathematical foundations, look at Turing, the work in '36, where he defined the class of computable functions. I'm not going to discuss that work, crucial as it is discussed in the book in outline. But then in 1950, Turing came back. He spent the war years working on encryption at Bletchley Park. It's no doubt a story well known to you. But in 50, he wrote a very important article on mind called Intelligent Machines, which got published exactly as artificial intelligence was starting off, and his article played a major role in defining some of its issues. And in this article, I think, in my opinion, very wisely, he treats the question of what general intelligence is as essentially impossible to answer and possibly bordering on the meaningless. But he does suggest an operational criterion, which is a Turing test, and that involves conversation with a hidden interlocutor behind a curtain, whether it be a person or someone or a machine. And the criterion is that if the machine can fool you into thinking it's a human, a good 70% of the time it qualifies as intelligent, at least by description, if not by fact. I'm not going to talk a lot about a Turing test. It's a really interesting issue that I do discuss in the book, but my concern here is more to look at the history. The first electronic digital computers were constructed both in Britain and in the US. There was one built here in 43 and then in Manchester in 47 or 8, and ENIAC was built in Pennsylvania in 48. So these were the first digital computers. Earlier prototypes of digital computing devices came out of Bletchley Park. So you see that AI was very much part of the foundation of computer science. The main event, which I think defines AI as a discipline, took place in '56 when John McCarthy, a very important computer scientist, the guy who created Lisp. For those of you, I know you think the only programming language in the world is Python, and there was never anything else except maybe ancient Greek and Latin. But in fact, there were many computer languages, and one of the most important, perhaps the first important functional programming language was Lisp, and McCarthy created it. He convened a seminar in Dartmouth in the summer of '56, and it was devoted to AI, and it involved a really fascinating collection of people who then were, there wasn't a discipline of computer science. They were essentially mathematicians, psychologists, neuroscientists, electrical engineers, and included people like Shannon, Claude Shannon, the information theorist, and Rosenblatt and other people who later came to be identified with the very foundations of AI.
I think you have to think.
Sorry?
You have to think. The slides here are well too advanced.
Hold on.
Yeah.
So, here. Okay. Nah, I've got to keep them straight. Right brain, left brain phenomena here. Okay, so it's possible, I think, to make a distinction, and it's already implicit in Turing's work, but it became explicit later on in work of computer scientists, between what we call strong AI and weak AI. So strong AI looks to build a computational model of general intelligence. You'll hear a lot of work, a lot of discussion about whether current large language models embody general intelligence. Okay, so that is basically the notion of strong AI, where essentially what that means is that a model like that will, amongst other things, be able to do whatever you would attribute to an intelligent human, that is, normally intelligent human. Acquire native fluency in a natural language, engage in unrestricted dialogue over any domain, recognize different types of objects and events in the world, reason about them, assign probability values to events, and infer conclusions from premises, amongst other things. The weak AI approach is different. It seeks to build systems that achieve at least human levels of performance for specific task applications. And despite much of the rhetoric that you will hear, some of it from computer scientists, one might add, is really work in weak AI. Most of the systems that have been built are very much task and domain focused, so the weak AI approach has been the kind of dominant leading approach in AI until today, and it's the one that I'm going to focus on, although I will talk about general intelligence in the next lecture. What about methods and models? In the early years, actually neural networks emerged first and very early on as an approach to AI, and the work was done actually by McCulloch and Pittens, who were neurophysiologists and mathematicians. And they presented the first, this was in '43 in the middle of the war, presented the first formalized model of a neural network, which was a mathematical model intended to model a human brain. And their neurons are information processing unit that take binary inputs in the form of 0 and 1. They have activation functions to the inputs that cause them to produce binary inputs depending on the kind of binary outputs, depending on the kind of inputs they get. And the units that correspond, the units that make up this kind of network correspond to the truth functions or the logic gates of a propositional logic, which of course became the circuitry of a computer, a digital computer. And the networks of the neurons can be used to encode and compute computable functions. Rosenblatt in '57 and '59 was an American psychologist, mathematical psychologist, actually introduced the perceptron, which became the foundation for work on learning with neural networks. He was actually, again, inspired by a correspondence to the human brain, but this was less significant in his work than it was in the earlier work. The perceptron consists of a neuron that receives inputs, x1 to xn, to which weights are assigned. And these weights are summed in a weighted bias B, which is intended to compensate for background noise on the inputs. The bias corresponds, as I said, to activation noise. And the information is passed to a binary activation function that determines whether to produce a positive output Y if the total summed weights are above a threshold and 0 otherwise. Now there are some interest. Here's a kind of diagram from Honkala of what a Rosenblatt perceptron looks like, and you can see quite clearly that it follows the general description that I gave you. With inputs x1 through xn, the bias function here at B, the output function, and giving you y as the actual output. There's some problems with perceptrons that were noted early on by Minsky, Marvin Minsky and Papert in '69 in a fairly major book. They show that Rosenblatt perceptrons can't learn nonlinear functions. A linear function is one whose values, range of values, provide a straight line on a graph at any given angle. The example of a function which can't be modeled by a linear function is a Boolean exclusive OR, which would hold if the two arguments A and B, one has to be true but not both. So an example would be if you come to a T-junction in a road, you can go right or left, but you can't go both. Although I've seen some drivers attempt. Okay, so although now they thought this was a knockdown argument against perceptrons, what they didn't sort of recognize at the time was that single perceptrons can't encode exclusive OR, but you can learn such functions with a multi-layer perceptron network. That is, if you have several layers. So one can learn the OR and the other can learn the NOT. And this is an example of a multi-feed-forward network. You can also have nonlinear functions, in particular things like sigmoid functions, which this sort of funny S-shaped thing represents, and the S-shape is an indication of its geometric form of the values that it produces, which is nonlinear. So this is an example of a multi-layer feed-forward neural network of a fairly basic kind that comes from Gupta in 2017. Then the question of how you train these things. So the weights for neural networks are generally set as random values, but then they're corrected incrementally as data gets fed into the device for training. And what you have is the error rate of the network is going to be calculated as a gradient. Think of that as a line going down, which is the value of the loss function. The training involves proceeding down the slope of the function by incremental correction until you get a statistically estimated optimal point, which is the best point you can get for correcting the mistakes, and that's called stochastic gradient descent. So the two guys who won the Nobel Prize in physics, one is Jeff Hinton, who's at the University of Toronto. He and I switched cities. I'm a Canadian from Toronto, and he is a Brit from London. He was originally at UCL, and my father taught at University of Toronto, and I was there on sabbatical, and we switched cities, and he didn't want to switch back. He was one of the pioneers of gradient descent and also something called backpropagation, which is where you feed the difference between a desired output of a network backwards along the connections among the units to calculate updates for the weights so that it comes closer along the gradient function to what you want the thing to give you. So Hinton did pioneering work in this area. He didn't create backpropagation or gradient descent, but he did refine and develop its application and popularize it. Okay. Now, simple multi-layer feed-forward networks were the foundation of neural network computing, sometimes called connectionism, for many years. They achieved a lot of success in classifying tasks such as identifying images and optical characters. This was like in the 60s and 70s. The problem was that they lacked a memory for recording output recording output values of units in previous processing steps of the network. They didn't have memory. That was a problem. And the result was that they were not able to reliably track relations between disparate or non-adjacent elements of an input string, in particular where those span distances over a sequence. So you get this kind of problem if you look at the brackets. So the lower the number, the higher the distance, the greater the distance between, say, the one here, right? And the higher the number, the more embedded the thing is. So that kind of structure, this represents a structure both of embedding and of long distance dependence. And these kinds of things were beyond the reach of simple feed-forward neural networks. So the limitations of these networks, and these were just some of them, caused AI researchers in the 60s to start exploring a variety of rule-based symbolic systems. These included scripts and frames, which were ways of sort of modeling paradigms of action and objects, non-monotonic logics, and fuzzy logic and set theory, constraint satisfaction solvers, which are based on propositional logic, horn clause rewrite systems, which provided the basis for definite clause grammars, which drove all sorts of computing systems involved in natural language processing. They sought to model reasoning and natural language through handcrafted systems of constraints and generative rules. So that was kind of the tradition I was raised in. While these things captured important aspects of inference and linguistic knowledge, the systems that they produced were all small scale, and this was virtually of necessity because they were built largely by hand. And every time you encountered a new case, you had to add new devices. There was no learning component unless it was externally added. It wasn't intrinsic to these symbolic systems. And that's why they didn't scale up. Another important strand of work in early AI, which continues to be influential, is probabilistic methods. And this involves using a probability theory, which itself is a kind of logic, intended to reason about uncertainty and the nature of belief about likelihood of alternative states of affairs, to model reasoning as well as various phenomena in the world. So it's intended to accommodate revision of belief through a dynamic upgrade system, and it produces a recomputation of probabilities throughout the whole system when you get new information. The most influential school of probability within AI is Bayesian, and one application is in building Bayesian networks of belief. And this was done by various people. One influential paper that describes it is Pearl and Russell. And this was used to model inference and belief in AI. The Markov models were used in natural language processing. They're discussed in Jarofsky and Martin in their book, which is online, and it's about to come out, but it's in manuscript form on natural language processing. And they fueled n-grams, which we'll see a diagram of in a minute, where an n-gram predicts the ith item of a sequence on the basis of its I minus n items. So you can build a whole probability model by sampling a corpus. And then you get Bayesian hidden Markov models, which are more powerful because they predict the occurrence of unseen items or events, given occurrence of those observed events and beliefs concerning their likelihood in a corpus where you're using Bayes' theorem. And I'm not going to give you Bayes' theorem now. If you don't know it, it's easy enough to find, and it's in the book. There are two diagrams. The first one on top is a simple trigram model. Below it, you get a hidden Markov model for computing word classes. The advantages here is that you can get a certain amount of long-distance dependency, but that depends on the size of the n-gram. The longer it is, the more dependency you can get, and similarly with the hidden Markov model. But then the rarer the occurrence of those strings will be in a corpus. The shorter it is, the more frequent they are, the easier it is to get a reliable model. But then, of course, the shorter the dependencies. Now, all of this brings us to the point that what you see through to the 60s and 70s is a field with a whole range, a multiplicity of radically different approaches and models, and within each approach there are sub-approaches. Each time an approach became popular, you get a kind of heady optimism concerning the prospects of solving a whole range of AI problems, very often highly unrealistic with a lot of hype. And this would be followed by disappointment, where you would get what was called an AI winter. So you get AI summers and AI winters. You get a kind of meteorology of AI. And this was very common. In fact, one of the reasons I came to Britain and to London was that the AI department in T.J. Watson was closing down. And although I was able to stay, I decided I wasn't interested. I wanted to continue doing AI and NLP. Little did I know what was on the horizon just a few years afterwards. You find that after the burst of enthusiasm in the 50s and the 60s, there were a series of very skeptical assessments that produced an AI winter. This was in the 70s and 80s. I remember coming into computer science departments and cognitive science departments, and people just laughed at AI, thought it was not a serious field. It was the stuff you pawned off on graduate students who you didn't expect to have engineering skills, who were good for blue sky research. I guess I was one. Anyway, the assessments that produced this kind of skepticism started fairly early. There's Bar Hillel, Yeshua Bar Hillel was a philosopher and a logician who wrote a very influential critique of machine translation, and then was followed in '66 by what's called the ALPAC report, was a federal report on machine translation in the States. It more or less trashed the possibility of high-quality automatic machine translation and said at best there could be heavily human-assisted translation or machine-assisted human translation. There was a Minsky-Papert assault on neural networks. And then in Britain, there was a Cambridge report authored by a mathematician called Lighthill in '73 who said he didn't see much coming out of AI. That was the long and the short of it. It was a little more sophisticated than that. These cumulatively helped to basically produce a major AI winter. Now, interest in neural networks then picked up again in the late 80s when new methods of training emerged. But also a crucial factor, which we'll come to in a second, is that more extensive digital resources for training and new network architectures and powerful hardware all converged to produce a turbocharge for neural networks in the late 80s. So the hardware innovations which happened, it's worth looking back on the 50s and 60s. The guy I worked with in IBM, who was a very gifted natural language processing person, told me that his supervisor in math and computer science at Yale told him that he didn't trust a computer you couldn't get into. Computers were the size of rooms. They ran on vacuum tubes. Data was stored on magnetic tape, and you did programming by punching cards. It's very difficult to imagine this, but it's actually not, in the scheme of things, all that long ago. Intel then produced the first microchip in '71, and this already created a small transformation of the computer industry, shrinking the size of the machines, but also vastly increasing the processing power and memory of computing. In 1999, a major hardware change came when the first GPU, graphical processing unit, was created by NVIDIA. It was called the GeForce 256. These are parallel processing units, which, unlike central CPUs, they actually consist of multiple processing units. They were designed originally to power computer games, which needed very rapid computation to sustain credible graphics. But then very quickly, everyone else realized, hey, that would be really good for neural networks, for training them and running them. And so GPUs became standard equipment fairly quickly. And then Google deployed its first tensor processing unit, which is a specialized unit on the cloud and the Google server in 2015. And that's a specialized processing unit which performs linear algebra operations and multiplication of matrices, which again speeded up work in neural networks, which rely on multiplication of matrices involving vectors. Okay. But then there's the issue of digital resources. So in the early years of AI, machine-readable text, other sorts of stuff, it almost didn't exist. There was no internet. What did you have? The information that was required to train a neural network and statistical models, they all had to be handcrafted and fed into the machine. The first major statistical model for machine translation was done at IBM in 1990 when I was there, not by me, but by the speech group. And it relied on the Hansard record of parliamentary proceedings in Canada, which happened to be in English and French because Canada's bilingual English and French. That was the first major piece of digital data that could drive a system and get something resembling wide coverage. So the innovation in processing hardware and the digitalization of data provided the basis for progress that hadn't been seen before. And this all started to coalesce between 90 and 2005, when the internet became itself a major source of digital content for training. Deep learning, however, in the end turned on radical changes in the design of neural networks. And those design changes are what really produced the revolution, the first phase of the revolution in AI. Although the spread of digital content and the hardware changes were crucial as historical foundations for making that architecture practical. So the first change in neural networks that addressed the problem of long-distance dependencies in memory was Jeff Ellman in 1990, introduced something called a recurrent neural network. We'll see what it looks like graphically in a minute. And it's a sequential processing system with a memory. It was built for natural language processing.
Just want my coffee.
Simple RNNs don't filter or control the information they pass. They just pass in bulk information from one processing state to another. And that rendered their accuracy fairly limited. So then you got something called long short-term memory networks, which had filtering devices by Hochreiter and Schmittelberger in '97, where each of the processing units applies one of three functions to input vectors. All the information is represented as sequences of numbers, vectors, and their filtering gates are provided by these functions, which determines which information gets passed on to the next phase. And then backpropagation, which I described earlier, is used for training an RNN. The problem there is that when backpropagation applies to these systems, RNNs and feed-forward networks, it creates what's called an exploding or vanishing gradient problem, which means that the information necessary that the loss function needs to compute a correction either explodes or vanishes. And this was a serious problem in this phase. There's an example of a simple recurrent network graphically to see how it works. And there's an example of an LSTM where you see in the middle cell or time step the application of these functions, 2 sigma, 3 sigma functions in a hyperbolic tangent or tan H function, each one deciding which part of the input gets passed on to the next phase of the processing of the input in this LSTM. Then you had another kind of neural network, and this first phase of the deep learning revolution called convolutional neural networks, and they were developed by Jan LeCun, who's still very active, and this was around 2020 that he describes them in detail, but they were around before. They identify a feature map. They extract it. They don't have to annotate the data with it. They extract a feature map. From input, things like pixels would be examples of the kind of data they use. By recognizing subcomponents, they then perform an operation called pooling, which reduces the dimensions of the features to get a compressed map so it doesn't explode. And they render it stable under variations. And then you get successive applications of these operations of convolution and pooling to produce ever higher representations of the object in the data. So you start from real simple input data at that kind of a basic level of, say, pixel representations for an image, and you build up to geometric representations of shapes and angles. And then you get what's called a softmax function, which produces a probability distribution over different possible categories for the vector in order to classify the output. And CNNs were giving good results for visual classification tasks and speech recognition already by the around 2015. There's a diagram which shows you the different phases of a CNN. There's a kind of classic CNN diagram from Saha in 2015. Now, much of the power initially of the linguistic versions of neural networks comes from something called word embeddings. And these are vector representations of, in the first case, linguistic data. In particular, what they represent are distributional patterns of words in a more abstract form, compressed. And they're known as embeddings, and they express, as I said, distributional relations among elements of the data. In the case of the words, they provide a conceptual map, so they capture various kinds of meaning relations as well as certain syntactic patterns, which they extract automatically from the data. And there are various algorithms for building such embeddings. One of the earliest was word2vec, and then you had things like glove, and now much more powerful embeddings. These are the things on which neural networks of any type are pre-trained. They encode semantic and syntactic relations as extracted from a training corpora or set of training corpora. They also are multimodal these days, which means they expand the power of the DNN because they express distributions not only of words but of any data point amongst other data points. So it gets a general conceptual map of distribution of different kinds of data across modalities. So things like ChatGPT or BERT, these kinds of very powerful transformers, which we'll come to in a second, generally have multimodal, they're pre-trained on multimodal embeddings. Now, going back to the earlier first generation of RNNs and CNNs, early on, around 2015, Badenow and his colleagues introduced an additional layer called attention between input and output of a DNN. And what it does is it produces a dynamic context vector as an interface between the encryption or encoding part of the, not encryption, encoding part of the network and the output or decoding part. And through attention, it essentially renders this context vector not static but dynamic in such a way that it's able to keep track of different phases of computation and align the relations between the input and the output, the desired output of the system. So it essentially preserves information from each encoded hidden state in a way that it didn't in non-attention systems. And it assigns different weights to these states on the basis of their relations to the output of the decoder. So this gives you a much more refined dynamic system of balancing the elements of an output to that of a desired input. The attentional context vector learns to align the weights very quickly, and that gives it its power. And there's a diagram where you see the broken line giving you the intentional layer, which is the context vector. This produced the idea of generalizing attention so that basically all the elements, all the units of a neural network consisted only of intentional heads came Vaswani in 2017, and that's when we got transformers. So although they've been with us now for 7 years, that's not a very long time. But in that period, they've developed very quickly. Let's just review very quickly what transformers are. So in general terms, they're encoder deep neural networks that consist entirely of blocks of multi-headed attention units. That is, all they do is compute attention for each element of the unit. Then they're connected, these different heads, by normalization and feed-forward layers. The fact that you have normalization throughout the system and that the system keeps track of all the different phases of the computation through attention means you don't have exploding or vanishing gradient problems with transformers as you did from earlier DNNs. This is a major advance. In addition, each block of the multi-headed self-attention unit, self-attention means paying attention to the relations between the elements of an input. The fact that each block in a multi-headed attention unit, or set of units, is dedicated, is trained separately and dedicated to a different dimension of information concerning its input, gives the system a great deal of multiplicity and subtlety in its ability to pick out different aspects of connections amongst the elements in an input represented as vectors. So in this way, the transformer can identify patterns and connections among elements of the data on which it's pre-trained, which earlier systems simply couldn't. You get multidimensionality of features here that far transcends the recognition abilities, the learning abilities of earlier systems. So they're generally far more successful than RNNs and CNNs in recognizing long-distance relations across much greater distances. And there's a diagrammatic representation of a transformer architecture, but in the interest of time, I will skip over it, because otherwise I won't have time to, either that or I'll bore you, or both. Okay, so fine-tuning is an interesting feature of transformers that all of you who've worked in the field know about, because you spend most of your time doing it. The transformers are pre-trained on large data sets, and we saw that gives us embeddings, but they can be fine-tuned for specific applications, which means after they're pre-trained, they come packaged. You can add new dedicated layers of attention heads, or you could retrain some of those that are already there with very specialized data sets. That's a kind of focused learning. It can be supervised if it's annotated. And that's a procedure for customizing the model for a particular domain or a set of tasks. Transformers can be efficiently trained because the blocks of attention are trained independently and in parallel. And because, as we've already noted, their normalization layers and the fact that they retain information from previous levels means they avoid vanishing and exploding gradient problems. Now, the multimodal embeddings are interesting because the transformers can accommodate different kinds of data from different domains, say text, auditory files, visual information, without changing their basic architecture. It's not necessary to build special purposes devices. It's simply necessary to make sure that they're trained with the right data, either through pre-training or through fine-tuning. And the attention heads can recognize connections amongst these data points as represented in vectors across these modalities in the same way as they do as if terms or words linguistic input. So we have, with transformers, a very serious breakthrough in deep learning, and that's why it's the second phase. It deserves to be recognized as the second phase in the deep learning revolution. Now, these systems are driving large data models that yield really impressive results currently on display in areas of AI. Now, despite successes, there are a number of interesting comments that have been raised by skeptics. So Emily Bender and colleagues and Noam Chomsky and colleagues in successive papers have claimed that large language models which transformers support are nothing more than stochastic parrots. Rather striking turn of phrase, which means that they only return versions of the data on which they're pre-trained. So is this claim correct? Well, in fact, it's false. I mean, and it's not only false, it's grievously false, meaning it simply misrepresents the facts, which are open to inspection. Why do I say that? Because we know that these systems, that is, large language models where they can be multimodal and hence language is extended, transformers can identify abnormalities in X-rays for diagnostic purposes. They predict new molecular structures for proteins. The two people who won the Nobel Prize for biochemistry or for chemistry used these models to predict new protein structures. They pioneered that. These were previously unknown proteins. They learn complex verbal commands in new virtual environments. They identify scenes in graphic images and produce accurate descriptions of the scenes. They generate computer code to solve difficult problems and help out students who don't want to do their own coding. And they generate novel proofs of mathematical theorems for mathematicians who are tired or lazy. Now, the inferences that sustain these achievements can't be reduced to simple variations of previously encountered regularities in data. They're picking up generalizations and inductive patterns that humans can't or don't. So to dismiss them as stochastic parrots is simply to misrepresent the facts in a fairly, which suggests a lack of familiarity with the system. So there are many criticisms to make of these models, but that's not one of them. Here's an example of a GPT-4 system. This is from the paper by OpenAI in 2023, where you see this funny sequence of three images where an old-style VGA connection is attached to a modern smartphone like this. And the prompt asks to describe it, each panel in the sequence, and describe and also to point out the source of humor, and the system does it. So in the end, it says the humor is in the image comes from the absurdity of plugging a large, outdated VGA connector into a small, modern smartphone charging post instead of using an appropriate USB-C connection. Now, whether this is canned data or not, I don't know, but it appears in the paper, and the performance of ChatGPT-4 does suggest it would be able to do this task. Now, that's hardly a stochastic parrot. One of the problems that does come along with these systems is hallucination. They provide extremely fluent, plausible text, which is very often entirely fictional. That's because they are, even when grounded in non-linguistic data, constrained only by probability distributions on what the most likely continuation of a sequence should be. So truth and accuracy are not constraints built into the system. This has produced some really weird effects. In fact, there's a famous case reported in the New York Times in '23 of an American lawyer, I believe it was in New York, who used GPT-3 to find legal precedents for a case and found 6 immaculately formatted cases, which he then took into court. When the judge checked them out, they were all fabricated. Not only was the case dismissed, but the lawyer was suspended. So be careful with your use of these systems. Now, let's look very briefly as a sort of final component here at some of the beneficial applications of these systems. We'll have enough time next week to look at some of, and the week after, the dangers which these systems produce. There'll be more the third one, where the real dangers are discussed. So one is information retrieval. So large language models serve as question and answer chatbots, and they do that without altering their architecture. So those of you who are using search engines like Google, which used to be special purpose statistically driven, are now increasingly relying on actual large language models to generate accurate answers where you don't get precise keyword matching. Because of the word embeddings being fairly abstract, there's a lot of paraphrase relation between the documents they use as their source and the information you're getting. The replies are fluent, and the content doesn't have to correspond to the words and phrases in the documents. They can describe visual scenes, they can read charts, they can process graphs, they can do math. Retrieval augmented generation is a reasonably recent procedure for fine-tuning transformers in order to access current and online data to update the information that they have at their disposal and presumably to improve their reliability. We'll get to that problem of reliability in the third lecture. It doesn't solve it, the problem of verification, because the online sources are as liable to corruption as the training data. That is, they could be themselves fictional. Machine translation. So machine translation has actually exploded as an area of second generation, second phase neural network success. So as recently as 5-6 years ago, the quality of translation was fairly low across even reasonably closely related languages with heavy digital content, and now it's very high. And I can tell you all sorts of research stories about being shocked at how well it's progressed in the last 5 years, but the move over to transformers from earlier systems has made a huge difference. And it's also improving for low-resourced languages, and that's for technical reasons. Those are languages where there's a dearth or absence of digital data for training. I'll skip over some of the technical material here. What I'll point out is that there's something called decoder-only generative transformers. Those are ones which essentially train only on one language for a language model, and then through fine-tuning on a very limited set of paired sentences from a target and a source language, achieve accuracy very quickly on machine translation, and they work really nicely for low-resource languages. This is still very much in development, but it shows promise for solving the problem of low-resource languages, not only in machine translation, but in a whole set of other applications. Automatic speech recognition and text-to-speech. These are areas which were part of the founding era of AI, but with large language models, performance and speech recognition and text-to-speech generation has picked up greatly. The systems are used in a wide variety of applications: dialogue management, telephone interfaces, automatic video captioning, and voice-activated assistants. We get Siri and Alexa now replacing their previous drivers with transformers. Many of the applications, although developed years ago with statistical language model processing models with partial accuracy, are now performing at something close to human competence. Code generation I already mentioned, and it's actually a version of the machine translation task where you're translating between natural language and code. And the level of success is quite high. You get increasingly high quality code in languages other than Python, as well as Python, using natural language, using large language models. And some of these work in decoder-only mode, that is with a few supervised examples of pairing for fine-tuning. They can produce adequate code across a whole set of languages. And they can also be used as coding assistants where they correct mistakes. Automatic theorem proving, I mentioned this as an area that was important since the 50s. Normally, in the past, what you did is you implemented a rule-based theorem prover that encoded a particular mathematical or logical system and used it to test test propositions as theorems or sentences. Currently, large language models are simply trained on large sets of proofs, some of them annotated for correctness, and they're designed to generate probability distributions over the continuation of subgoals in the proof. Strikingly, some of these these theorem provers have improved on human proofs. For certain difficult theorems, they've provided shorter and more economical proofs over those which mathematicians have come up with. So you might think this is a sort of interesting theoretical issue, but in fact, it has practical significance because if you think that formal results are the foundations of engineering and in physics, and that without some of these results, your engineering won't be sound, theorem proving does have practical significance. It can also be used as a form of constraint satisfaction solving. Okay, medical and bioinformatic applications. So we've already mentioned these. Visual transformers are supporting diagnostics for pathology, which have achieved striking levels of success. They're outperforming human diagnosticians on a whole range of tasks. Multimodal transformers generate written medical reports from images, and that's a version of the machine translation task. Transformers have revolutionized prediction of protein properties. We saw that in bioinformatics, but also in pharmacology. So they are able to predict the effects of various kinds of proteins and acids on viruses and bacteria, and help with the development of medications. And they model patterns of cell development, genetic development, so they're very useful for computational biology. These are not stochastic parrots, unless you have an unusual parrot. The final thing is music and fine arts. So increasingly, musicians and graphic artists and visual artists and filmmakers are starting to use deep learning systems to generate musical compositions, films, and photographs and visual images, plastic arts. In addition, some of the musical compositions, by the way, have been rated highly not only according to objective performance metrics of things like melody, consistency, and rhythm, but also on human evaluation, which isn't to say that they're going to replace human composers. Much of the more interesting experiments that I've read about involve collaboration between human composers and these systems, which initiate riffs that the human composer then takes over and develops. As I said, we've seen them generating images for films and other artistic production, but they're also, and it is a really interesting application, they're used discriminatively as classifiers for paintings as well as literary works to confirm or refute the artist's identity, the author's authorship, and to assess the authenticity of a work, so that they are an important assistant for avoiding fraud and fake. So let me now, I'm still within my hour, come up to some conclusions. I don't mean to give you a Panglossian view. I'm highlighting the good so that when we come to the problems, I won't be accused of having overlooked the benefits. In the third lecture, I will go to town on all of the very serious dangers we need to worry about. And they are serious. They're things to worry about. The second lecture will talk about things which I don't think are serious problems, but people have managed to scare themselves with it. Okay, so here's some conclusions. The early period of AI, we saw the proliferation of a whole range of approaches to learning and representation, from feed-forward networks through rule-based and symbolic systems, to logics, to probability theories, and statistically driven model. This is very much indicative of a young and immature field, where it's experimenting with new methods and looking for approaches that will work. Hardware and digital data limitations made it virtually impossible to develop wide coverage systems. You just didn't have the processing power or the data to do it. Once we had serious hardware innovation and data availability, digital data access, and radical changes in neural networks, we then got a deep learning revolution, which hit at the beginning of this century. And it came in two phases. The first giving us CNNs and RNNs, CNNs and RNNs. And then moving on with attention to transformers and large language models that they drive. And they've achieved striking performance over the initial generation of DNNs. Now, a central element of the progress is the capacity of transformers to transfer high accuracy learning to new tasks and domains with minimal training and with the same architecture. So the age of building special purpose systems has more or less receded. And we now use a kind of common architecture which we can adapt to virtually not any, but very large range of tasks, which makes it much easier once the initial training has been done, or pre-training, to get what's called transfer learning and one-shot or few-shot learning, where we apply the same device to a whole set of new applications and tasks. And this is an impressive result. It doesn't mean this is general intelligence. It's very far from it. But it does mean that the systems are capable of learning in a particularly impressive way. So this is a good part of AI. The other stuff will come later. So let me stop here and take your questions and any disagreements or issues you want to raise. Yeah.
Hi, so I
You have to
really
speak
enjoyed
up.
your talk.
Sorry.
Okay. I really enjoyed your talk, but I do have two questions.
Sure.
The first one is, LLMs like ChatGPT, they generate different outputs even though the input might be the same. Is there any way to trace back to an input that was generated a specific output? And my second question is your book available on Audible?
Oh, okay. The book, I mean, literally the last line of the book was written a half hour before I came here, and it'll be coming out next year. However, if you're really interested and you send me your email, I will send you the manuscript, but it's not published. So it will be published next year. I'm happy to share the manuscript on the condition that you give me comments for it and things like that. The first question is a really interesting one. It's, can you reverse engineer a large language model so that you can reclaim the input or know what input it was trained on? In most cases, you can't. And this is an interesting problem. The reason is that there's a good formal, kind of technical mathematical reason for it, which is that these systems use nonlinear functions. And hence they're what are called non-compositional, which means you cannot accurately predict the output on the basis of the components of the input in a given function. So the fact that these functions are nonlinear means that there's, half the time we don't know what these things are doing and why. We can only use indirect methods. So no, we cannot reconstruct input from output alone. Or even when we look at the device, it's very difficult to see how it managed to come up with the generalizations that it did. So there's a high degree of opacity in the system. And that's one of the drawbacks of this, the larger and more complex the system is, and in a deep neural network, particularly large transformers, the less transparent is the learning process. So we know we designed it, but we don't know exactly how it's extracting generalizations it is, and we certainly can't reclaim the exact input that it did it from.
I think it's also fair to say that even if we were able to
You have to
reverse...
speak up because there's a room behind you.
Okay, yes. I think it's fair to say that even if we were able to reverse engineering, while we cannot, because we did not train the models, we do not know on what input they were trained on. Okay, so as long as we give like third-party companies the right to sell us back our own human inputs, we will never be able to know on what exactly training set elicit a particular response.
I will get to the issue of property rights and copyright infringement involved in the training. Don't worry, these guys are not going to be giving you up. There's a question online. DevDot, you had something. Please unmute yourself and ask me, and I will convey it.
Yeah, hi. So,
Yeah.
just comment on two of the applications you gave towards the end. So you mentioned the Nobel Prize for the protein folding.
Yes.
And the protein folding, I would say that is not an achievement of LLMs. It's or transformers. So that's the AlphaFold. That's the AlphaFold program. So that's quite a different technique.
Mm-hmm.
And then the second comment I had was about you suggested that LLMs could be used fruitfully for information retrieval. And I would say that I would wonder about that, because I mean they're hallucinating and they're going to produce all kinds of garbage as well. And you mentioned the retrieval augmented, the ROC system, retrieval augmented systems as something that could mitigate the issue somewhat. So yeah, I mean it could be used with some caveats like that, but in general for factual fact retrieval, I think they're not particularly well suited for that, because they're after all generating text from a probability distribution, and that's not going to be only factual.
Did everybody hear these questions? No. Okay, so let me repeat them. This is Dafta Dubashi, is my friend and colleague from Chalmers, where he heads the deep learning or the machine learning group in computer science at Chalmers in Gothenburg. And he points out that the Nobel Prize that was awarded to the chemists was for work they did with a large language model system. It was a deep learning system, but not a large language model for predicting protein folding. I accept the correction. He's more expert in this than I am. The second point he made is that RAG, this system of retrieval augmented generation, is not a reliable way of verifying content and information retrieval, and I entirely agree. I tried to give the caveat, I should have given it stronger. It will, if you trust the source and solve the problem of verification for a digital source, then it's fine. If you haven't, and a lot of yours, you can't distinguish between reliable and unreliable digital data online, then of course it's not going to solve the problem, and I entirely agree. So there's no points of disagreement there. Thank you for those comments. Anyone else? Yeah.
For the purposes of producing artificial intelligence, because if we are serious about it, we're going to have to mimic, to a greater or lesser extent, the person.
Sorry, I'm not entirely hearing you. You'll have to speak
Sorry,
up.
we're going to have to mimic the neural network to whatever extent that we're finding here. And how far would you say we are in understanding the psychology of the human brain and then the neural networks therein, so that we can at least mimic some of the functions that are in the human brain?
I don't agree that in order to achieve either general intelligence, which I think is a problem of a different kind, or task-specific or domain-specific intelligence, you need to reproduce the mechanisms that drive the human brain. I simply don't agree with that. In the same way that in order to fly, we don't have to produce flying machines that reproduce the flight of a bird or of a fly. We use helicopters or jets. And there are universal sets of principles of aerodynamics which come from physics, but we certainly don't have to use biological mechanisms as the only or necessary paradigm for achieving a task. This is the difference between weak and strong intelligence in part, which is that, weak and strong AI. Weak AI wants to solve a task. It's an engineering problem, and it will use the methods that succeed. So whether or not the formal graphs, which represent the neural networks, reproduce the brain circuitry is irrelevant. They might have been inspired that way. It's very questionable whether they look like that. I don't think it's reasonable to think that human brains consist of attention blocks. I really don't. But these work very well for computing. So I just don't see that either kinds of intelligence, if they're artificial intelligence, require us to reconstruct the organism, in this case the brain, through which our own intelligence emerged. Yeah.
Yeah, this might be covered by your next two lectures, but given that these large language models are being taught on the internet and more content from the internet is being generated by these, isn't there a risk of feedback and biases being
No, there's no question that that's happening. That a lot of the digital content now is itself generated by bots and chatbots and by AI systems, and that process will go on. So and that's a kind of corruption in a sense, because it's generated without a regard to verification or anything of that sort. So yes, it's a serious problem. Absolutely.
If I may add something. So I think it was also recently been demonstrated in publication that large language models that are trained exclusively on LLM-generated text collapse. Okay, after several iterations, completely collapse. So I'm not saying this is the situation with the internet, which still consists of human-generated natural text, but it is a serious concern, yeah.
Okay, Elizabeth, did you have a question online? You're muted. Can't hear you.
Yeah, I was just because you mentioned strong AI and weak AI, and I was wondering whether this notion of stochastic parrot that you also mentioned is more related to the idea that is to the strong AI, to the fact that these kind of procedures do not exactly manage to replicate what could be considered a strong AI. I'm not sure if my comment is clear. Because you mentioned stochastic parrots,
Oh,
right?
I see, yes. Well,
So I was wondering whether people using this stochastic parrot image
I see, okay.
think of it in terms of it's a stochastic parrot because actually it's not doing what we would say is a strong AI, like really doing intelligence, human intelligence, working. Was wondering.
That may be. I mean, there are two sources for that I'm thinking of. One is Emily Bender and her colleagues, who themselves are computational linguists and do have an understanding of how these devices work.
Yeah.
So it's not clear to me whether this was a general criticism that general intelligence had been reached or not. But there was an attempt, I think, on the part of Chomsky, who hasn't, and his colleagues, as far as I can see, any idea whatsoever of how deep learning works, to dismiss the entire field as essentially misguided. I think there's also a misunderstanding of statistics there, which is long-standing in his work. That is, if you look at the original criticism of statistical modeling in syntactic structures, the idea that unseen events which don't occur in a corpus have zero probability. I mean, people knew in 57 that was nonsense. In 53, you had smoothing from good Turing. So I think there's just amongst theoretical linguists of a certain variety, not all by any means, a very high degree of both dismissiveness but also misunderstanding and lack of familiarity with these kinds of systems. And therefore, I think when they make these statements, more often than not, it's because they haven't bothered to look at the literature and explore how these things work. I don't think that's the case with Emily Bender and her colleagues, who are themselves computational linguists. You may be right that she was criticizing the idea that these are agents of general intelligence. My own feeling is that she tended to kind of fall into the trap of seeing them as very simple inductive mechanisms, which they're not. But yes, there's certainly a very strong qualitative level of difference in sophistication in their understanding of how deep learning and AI work in those two cases. So I would take her work a lot more seriously.
Yeah, I was also thinking in terms of the contribution of Christianini, who talked about the fact that we took a shortcut in the recent years compared to the original goal of really having machines. But this is of course a very broad session. So, but anyway, thank you for your comment.
Thank you for your comments. Much appreciated.
Yeah.
Anything else? Yeah, Pat.
I want to speak up for parrots. Do you know, have you come across Alex the African Grey? Do you know that Pepperberg study?
Is this from Monty Python?
No. It's a real study, and it was annoying to Chomsky because there was allegedly syntax in the parrot's bit. Anyway.
Oh, yes, that's right.
So, sorry, the question I do have, so you are rightly pointing out that these models can do some really surprising kinds of generalization. But the way that you're explaining that to us is you're saying, look what it does. Can you give a characterization of what the class of generalizations it's making actually are? I mean, stochastic implies it's some kind of higher order statistical regularities that are detected in the...
It is computing likelihood of events. There's no question that these are sophisticated systems or devices for learning probability distributions over either classifications or the occurrence of tokens. There's no question of that. But they function a lot more effectively than previous statistical models. That has a lot to do with their internal architecture, which I tried to describe. When you use attention, you're able to, when you build a system entirely out of 10 blocks of attentional heads, which can attend to radically diverse strands of features and pick them up in a system, then you will see things that we can't simply by power of computation. We can't compute that fast, and we can't do it in parallel with the same number of units, whereas they can. Now, exactly how they do it is, at best, we can use indirect methods to kind of try and identify things like probes. Manning and Hewitt built a probe to try and show that ChatGPT and BERT have internalized a fair amount of natural language syntax, but it's implicit and distributed in the representation. The way these things represent knowledge is very different than the way that we think of it. At least in our conscious mind, we represent things very often in terms of rules. But these systems don't. They distribute knowledge over computing units with weights, and then readjust them through feedback. The surprising success, I think, has a lot to do with both architecture and computing power. And so that was the main message of the talk today. Yes, these are sophisticated statistical devices, but they're not parrots. They don't repeat what they've heard.
Neither did Alex.
Sorry?
Back to Alex the African Grey. Alex wasn't just repeating.
Even the parrots were slandered in the comments. Even the parrots were misrepresented. They're more creative than they were given credit for. I'm not surprised. Yeah. I mean, recent animal psychology work, you know this is your field, not mine, has shown far more subtle and sophisticated ability to learn communication systems and discrete units and combine them than we ever suspected. Right. I mean, for years we were told by MIT guys, linguists, not the other part of MIT, that, no, animals have call systems, they're discrete systems, they can't combine. It's not true. I mean, if you look at the evidence, it's not true. People started looking at the evidence and found that it doesn't apply. So you can either deny the evidence or you can say I was wrong. Yeah, there was another question, I think. Yeah, please.
Firstly, thank you for the...
You'll have to speak up. I'm partially, my hearing is not what it used to be when I was a young person.
Thank you for the lecture. And I have a question that might be so general, but is there any research or like topics that taking the other ways or alternative ways of using methods to train models instead of using neural networks?
Well, there are other models for AI. And a neural network is one of them. It happens to be dominant now because of its success. And there are other ways of training neural networks. Backpropagation and stochastic descent is only one of them. There are all sorts of training and learning methods that are used. I mean, one of the reasons that this guy Hinton got a Nobel Prize is he went through a whole set of them. It's a vast literature. So, what I presented you was a kind of leading headline on accepted methods and models, but there are other models and there are other methods. The stuff that I was referring to is kind of what's dominant now. But that doesn't mean people have stopped doing experiments with other methods or that other training procedures aren't in use. All I can do is suggest literature, and in my book I give all sorts of references to general books on AI that would cover that. Anything else? Yeah.
Thank you for your presentation. First of all, I have also probably a general question, but could you share your vision or idea what is lacked nowadays for making a strong, real AI?
Well, I mean, as you will
What is
discover,
absent?
what you will discover in the next years, I don't believe in strong AI.
Okay.
I don't think it's possible.
Okay.
I mean, I will try and give you reasons to believe that, but other people will disagree with me. I think it is essentially means, I guess at root I'm a Kantian. I don't think you can understand your own mind. I mean, I think the task of reconstructing, first we don't know what general intelligence consists in.
Yeah.
We just don't know. We know it when we see it. We can observe it on a case-by-case basis. We can tell when people are generally behave in an intelligent way, that in a way that we say they're generally intelligent agents. We can even imagine other creatures or agents behaving in a way that's generally intelligent. But we don't know what it is. We don't. It's not even a problem of a definition. We don't have, some kind of scientific theory for characterizing it. And I think basically it's pointless to try and build such a thing. I think that what we're doing now is a right approach, which is to build devices that handle increasing numbers of tasks with a unified architecture and be happy with that. But then there are all these terrible consequences that come from that we still have to control for. But as a project in engineering and in science, we also need to understand how these things actually learn. We don't understand the nature of the induction that these systems are actually using. We know their architecture, we can explain it mathematically. I've tried to summarize them. But we don't really know how they do systematic inference. And until we know that, we don't know how weak AI really works at this level. And once we know that, then maybe you can start asking questions about strong AI. Full confession, I don't believe in it. I don't believe it's a worthwhile thing. But other people, would disagree strongly. There was one question here, and then
I think Roger Penrose agrees with you.
Sorry?
From what I
I
understand.
can't hear you.
I think Roger Penrose agrees with you.
Oh, good. That's good. I'm glad to hear Roger Penrose agrees with me. Makes my day.
Can I ask, what could be the mathematical foundation for AGI?
Sorry?
The mathematical foundation for AGI, the general AI.
If we don't know what it is, how can we have a mathematical foundation for it?
Just for example, Fokker plug equation, these things is about the mathematical foundation of could be applied in the AGI.
Again, you're asking the wrong person. You're asking me to kind of tell you how to ground AI when I don't, I'm sorry, on general artificial intelligence when I don't believe in it. So I don't believe that it's a worthwhile or possible endeavor at this point anyway. And I think that weak AI is the only way we've made progress, and that'll continue to be the case for the foreseeable future. But it has to be tasked in domains. It's only there that we have clear metrics for evaluating success, and we use human performance for that. Yes, we can build systems that will defeat the grandmasters of Go and chess, but that's not general AI. It really isn't. So I'm not the person to answer your question. So you're asking for mathematical foundations for a discipline I think doesn't exist. So there's another question up there, yeah.
I'll try to form it. In the earlier slides, you were describing the neural networks, and it's just from an understanding point of view, and how you can reduce it down to something like a binary system. You gave sort of weighting to various aspects. I wondered, they seem to be like you've got a 0 or a 1, dependent on how it models that. And could you combine this with something which is more like a computing a qubit type sort of system where you've got...
Okay. Qubits, yeah.
It's not so straightforward where you
okay.
can say yes or no, and it all combines with the connectivity.
You're asking about quantum computing.
Well, I don't know if you could combine that with something which is made...
There are implementations of simple RNNs in quantum circuits. I mean, whether that is interesting or not is very much an open question. I'm not in any way an expert on quantum computing. What I know is largely from Scott Aronson's book, Quantum Computing from Democracies, and talking to friends who work in quantum computing. There have been attempts to implement at least simple RNNs and also LSTMs. The kinds of systems I've seen implemented are really basic and don't do very much. I suspect that's a result of the hardware limitations of quantum computing, which are still it's still in its infancy. Whether a more developed and reliable quantum computing circuit, where you didn't have problems of decoherence and instability, could support an interesting neural network, it could, because 0, 1 were old. This is the old system. The new system is using nonlinear and non-binary functions. So yeah, I mean, in principle, you could. And you probably could overcome, if you can finally got this running, some of the problems of exponential search. That would be the interesting thing. Search space becoming more tractable. But again, I mean, there's a lot of hype about quantum computing, but if you look at at least what I've read, what I'm told by colleagues, the state of the current quantum computing system, the largest one has 1,100 qubits. That's the IBM system. I mean, we're still pre-microchip age in terms of everything has to be cooled to near absolute zero. It's not a mature technology. It's not the kind of thing that is going to solve the problems we have right now. Eventually, maybe it will. But yeah, you definitely should be able to run a neural network or anything else on a quantum computer. In principle, I mean, it's a Turing machine. It's more of a Turing machine than a digital computer of the sort we have now. It's less restricted. It's closer to an infinite tape, not quite.
It may be a naive question. Would it not be able to generate something which is, if you like, non-human because of the fact that it's able to do things in parallel, but in a purely...
We're doing things in parallel now, but there we could do a lot more. I mean, we're doing a lot in parallel. That's a GPU is doing vast amounts of parallel computing. But here you could do stuff orders of magnitude more, faster and more complex. If such a thing were actually running, which it isn't. That's the crucial point. It isn't. And it's still a long way off. Anything else? Okay, well, thank you. I appreciate your patience. I hope you will come back for the second one, which will be less technical and much more controversial.
Thank you so much.